Okay, we're going to give this a shot. I've got my phone set up over some book towers, balanced on some rulers, shooting straight down onto the piece of paper so that you can kind of see what I'm writing. I'm not sure how smoothly I'm going to be able to do this, but we're going to try our best. This will just be a discussion of the geometry quiz that I sent back to you today, an explanation of some of the common errors and why those are mistaken. And we will maybe go into a little bit more detail in another video explaining the reason for the formulas being what they are rather than something else. You know, why do we say that the volume of a right prism is the area of the base times the height? Why do we say that the surface area of a cone is 1/2 of the perimeter of the cone times the slant length? Okay, all those things. So we'll basically kind of do proofs or at least explanations of why the formulas work, but we'll probably save that for another video. So I'm sorry you can't see me. It's not ideal, but doing the best that we can. So the first question on the quiz, the formula for the area of the circle, that was fine. Most people got that one all right. Just be careful that you don't confuse the area formula with the perimeter formula for a circle. And again, remember when we are talking about the perimeter of a circle, oh man, this is tough. The area of a circle is pi times the radius squared. Okay, and keep in mind, in the back of your mind, always with area and volume, keep in mind that area is a measure of the two-dimensional space that something takes up, some figure takes up, and volume is a measure of the three-dimensional space. So they're similar in the sense that we're talking about space, but there are different kinds of space here that we're talking about. So they don't mean exactly the same thing. So since area is two-dimensional, any area formula is going to have two variables being multiplied. And in the case of a circle, the only thing that really varies in a circle is the radius. So there's nothing else to multiply the radius by but itself. So you have r times r here, which is r squared. So you're always going to be looking for two things multiplied or one thing that is to the second power. You know, squaring is the power of 2. That's true for any area formula. So, you know, if we go down the list, well, that's for a circle, great. But if we look at the trapezoid formula, you know, the trapezoid is 1/2 of the average. It's the average of the bases, basically, or if you remember when we were learning about trapezoids, this is actually the formula for the median of a trapezoid. So we actually end up using that in the area formula. Again, we'll explain maybe why this is later. Times the height. So you have the base lengths, you average those, and that gives you a single length. So that's one of your variables. And then your second variable is the height of the trapezoid. So again, you're going to get something times something else, area. A parallelogram is the base of the parallelogram's length times the height. Okay, so again, two variables, 2 dimensions. Triangles, area is 1/2 of the base times the height squared. And you'll notice that there's some similarity here. These are pretty close, actually, to each other. So this one is the this one is the parallelogram. This is the formula for triangles. I'll let you think about why that might be the case, that they are similar. I bet you can come up with it. At least some of you should be able to come up with an explanation for why that is. Okay, the area of a sector of a circle. Again, I'm not going to explain this one now. We'll do that in another video, but it's also fairly intuitive once you understand what all this means. So it's x over 360 times pi r squared. And again, pi r squared, well, that's just the area of a circle. So we're taking a section of the circle. A sector is just a part of the circle. Based on this fraction, of the entire area. Okay, and x here in this formula, x is whatever the angle measure of that piece of pie, so to speak, is. So if I have a sector that looks like this, again, excuse my drawing, it's even worse than normal because I can't really see what I'm doing. X is this degree measure here. It's however big this arc is between the sides of this piece of pie, or this sector of the circle. Okay, and then lastly for the area formulas, we have for any regular polygon, again, we won't explain this too much for now, but it's 1/2 of the perimeter of the polygon times the apothem. And so we'll probably explain what this is in the next video. I won't go into it now, but we'll draw some polygons and we'll talk about the apothem in each of them. Okay, so note that in all of these, again, you have 2 dimensions. So here it's base 1 and base 2 is 1 dimension because they're only being added, they're not being multiplied. And then you have height. Here you have base times height. Here you have base times height. Here you have, again, r squared. Okay, and x here is a variable, yes, but it's not actually a dimension of length in the same way that these other things are. X here is a degree measure, and so it's not really a dimensional thing. Okay, it doesn't change the number of dimensions that we're dealing with. Here you have perimeter and apothem. So again, 2 dimensions. So for all area, it's going to give you formulas which are describing the amount of 2-dimensional space that something takes up. Be careful about your variables being lowercase or uppercase, okay? Because if normally in mathematics we have a limited number of variables and we sort of run out because there are so many things to represent in variable terms. So if I have a small r, that is always going to be the radius. And this is something that was, one of the later questions on the quiz, number 4 in part C. What do the following letters represent in all of these formulas? R, P, and H. These are all lowercase. Okay, lowercase r is the radius. Lowercase p is for the perimeter. And again, make sure you remember what perimeter is, or remind yourself. Perimeter is the distance around the edge of something. So on this paper, the perimeter is by taking this distance from this edge all the way to this edge, and then adding that to this length of this whole side, and then adding that to this length of the top side of the sheet of paper, and then adding that to the final side of the 4. So any distance around the edge of the shape, that's going to be its perimeter. And for circle, remember, a circle's perimeter has a special name. It's called the circumference, which literally means the around, bearing around, or taking something around something, so around the edge of the circle. And that has a special formula. You can't just add up side lengths because there are no sides in a circle. Again, the size of the perimeter is going to be based on the radius, and it's going to be 2 times pi times the radius. Okay, or you may have learned this as pi times the diameter of the circle based on, oops, I'm running out of space here, and paper. Because the diameter is just 2 times the radius. It's 2 radiuses put end to end, okay, so to speak. So keep that in mind. And then finally, h is the height of something. And be careful here. Height is not just what we always think of as height. What this really means in all of these formulas, both for area and for volume, the height is a altitude of some kind. Okay, so it's the distance from, remember your definition of altitude. If you don't, you can go back and look at this in your geometry book. Remind yourself, an altitude is a distance from an edge or a vertex perpendicular to the opposite side. Okay, and so that perpendicularity is key. In order to have a height in these formulas, we have to have what is actually an altitude. It has to be perpendicular to something else in the shape. Okay, so be careful about capitals and non-capitals because, for example, in all the area formulas, you have lowercase b. And the lowercase b is for the base of whatever shape it is we're dealing with. And the base here is just some side length that we choose to be the base. So like a parallelogram has 4 sides, and we know in parallelograms that these 2 sides are congruent and that the other set of opposite sides are congruent. Well, I can pick either one of those 2 lengths as the base. It doesn't really matter. It's just that whichever one I pick, the altitude then, or the height, is going to be different. It's going to be changed based on which one I pick as the base. So if I pick the long side as the base, so let's say this is the base of the parallelogram, then the altitude is going to be this height right here. This height is going to be the altitude. And that's what I want to use in my formula. If I pick the shorter side as the base, well, then the altitude is going to be something like this distance. Okay, this will be the perpendicular from this vertex to the line containing this opposite side here. And so again, the perpendicularity makes it the height, or makes it the altitude. But depending on which thing I pick as my base is going to change which dimension, or what the length of that altitude is going to be correspondingly. Okay, as long as I'm consistent, it's fine. Okay, so the base in all these formulas is just some side length that we have picked to be the base. So it's the same thing, same idea in a triangle. You've probably seen how that works before. The trapezoid has 2 bases, of course. It has its 2 parallel sides are the bases. But in the volume formulas, you have big B, as I've given it on the sheet. And now that I think about it, that was probably a mistake. I probably should have put A sub B like this instead. Or in other words, the area of the base, because that's what big B is meant to represent. And the base in a 3-dimensional shape is not the same thing as the base that we're talking about here. We're using the same word for it. Unfortunately, it's one of those things that is just easily confusing. It's the same word, but it does not mean the same thing, and so we should not use the same variable to represent it. In fact, what's probably more clear here is if you go to your sheet and you change all the capital B's to A sub B, because that really is standing for the area of the base. And the area of the base is going to depend on the shape that we have. So in a right prism, all of these formulas for volume, they all have sort of that in common, with the exception of a sphere. A sphere is kind of its own thing because of its circular nature. But all of these others, they're basically some form of that idea of, for volume, we need 3 dimensions. So we take the area of something, some base part of the shape, and we multiply it by the height of the shape. So the area already has 2 dimensions, like, for example, the base and the height of a parallelogram. So maybe our parallelogram is our base. So we've got 2 dimensions from that area that we found for the base, and then we multiply by the height, and that's our 3rd dimension. So we have 2, and then this would be 3. And so we have something times something times something will give us the volume. For example, in a rectangular prism, like a Kleenex box or a book, it doesn't look like this is going to all fit quite right. Let me pick the camera up for a minute. In a Kleenex box, you have any side you want, you can pick as the base, for example, but they're all rectangular, okay? Whichever side I pick as the base, whichever side I choose to rest the Kleenex box on, the base is going to be rectangular. And so the area formula for a rectangle is the length times the width of the rectangle. And then the only other thing that I need to complete this thing as a 3-dimensional shape is for it to have either depth, sometimes it's called depth, or we're calling it in these formulas, we're calling it height, or again, it's an altitude. It's a distance from a vertex perpendicular to the line containing the opposite side. Okay, and in this case, it's not only in the same plane, it's in a different plane, this opposite side. This bottom base, the bottom part of the Kleenex box, it's resting on is its base, and that's going to have the same area as this top base, at least in this particular shape, because this is a regular rectangular prism. So we multiply the area of the base times the height, and that gives us all three dimensions for our volume formula. So let's come back to the other examples of that. So in a right prism, that is the actual formula. It's the area of the base of the right prism times the height. Now, that shape for the base might be a rectangle, like in the Kleenex box, or it might be something else. It might be a parallelogram. Like I can have a parallelogram-shaped base, and then height or sides, actually let's do this down here, extending upward from that, or downward from that. In this case, I'm going to draw it downward. So I have a parallelogram base, and then I kind of draw in my altitudes, and I can complete my sides. Now, I know this looks kind of rectangular the way I've drawn it, but it doesn't really make any difference. Like if these are parallelograms, rectangles are parallelograms, in fact, right? Then I still have a right prism, okay? It's right prism because it's at right angles to the base. These are altitudes, these heights, these edges here. I could also have, a triangular base. I said I wasn't going to do all this now. I guess I just can't help myself. This is the kind of prism that you will see when they do demonstrations of light passing through a prism and being split into the colors of the rainbow. It's usually a triangular shaped prism, in fact. That's the simplest kind of right prism that we could have. So it could be, the base can be any of these shapes other than a circle, because for a circle, it's going to have a special name. The prism that has a circle as its base, we call a cylinder. And so the area of a circle, okay, the area of the base for a cylinder is pi r squared. And then we multiply that again, just like all the volume formulas, we're going to multiply that by the altitude of the thing, okay, by the height. So for a cylinder, it's the same idea as for a right prism. It's the area of the base times the height. But for a cylinder, we know that since the base is a circle, it's going to be pi r squared times the height. For a cone and a regular pyramid, it's still the same idea. It's something having to do with the area of the base times the height. But a cone comes to a point, right? Or a pyramid comes to a point. So is it going to have as much volume as a cylinder with the same base size? No. I'm going to try to make a cone here. I haven't done this in a while. Bear with me. Okay, so a cone. Oh, come on, almost got it. Cone is going to come to a point like this, okay, which obviously is not the same size as the circular base on the other end of the cone. Again, this is a piece of paper, so this doesn't work well, but if I cut this, maybe I can just do that actually. Scissors here. I'll cut this like so. And now, again, I'm going to have to pick up the phone. Now you can see that the base is, well, somewhat circular. Again, I would have to attach it just right to get it to be actually circular, but the idea is that now I have a circular base and then a point at the top. Okay, if this is a perfect cone, it's going to come to a perfect point. Mine is not holding together that well. So a cone can't have as much volume as a cylinder does. It's got to have something less than that. And again, the point now is not to prove why this is the case, but a cone is going to actually have 1/3 of the volume of a cylinder if the circle at the bottom of the cone is the same size in both the cylinder and the cone. The cone will have 1/3 of the volume. So it's 1/3 of basically you take the cylinder formula and you multiply it by 1/3. So it's 1/3 pi r squared times height. And for a regular pyramid, it's the same idea as the cone exactly, except a regular pyramid is using a right prism's base instead of a circular base. So it's the same formula as for a right prism, but again, it's going to be a third as much. Okay, so whatever the area of that base is, you multiply by the height, and then you multiply that by 1/3. And instead of the volume of a right prism, you will be getting the volume of a pyramid with the same size base. Okay, spheres are a little different, and actually this is not something that we can really prove too easily in geometry. You actually need calculus to sort of prove this, but it turns out that the area of a sphere is 4/3 pi r cubed. And the interesting thing to point out here is not so much the formula, because again, we can't really explain it too much. You just have to memorize this one. But you will notice that again, I have 3 multiplications for volume. Okay, radius times radius in a sphere gives me my 3 dimensions that I need. In the other ones, I have radius times height. It's still 3 dimensions. The area of the base, if it's depending on what the base is, you're going to have 2 dimensions from the area, and then the height gives you your 3rd dimension. Okay, so I hope that's clear, and I hope that helps you understand some of the corrections that we made. Some of you put, for the cone and the regular pyramid formula, you put it in terms of area of the base instead of writing out pi r squared or writing out pi r squared for the cylinder. Being a little bit more specific, which is okay. It shows that you understand the volume formula, but we're going to be as specific as we can be. Really, ultimately, this is what we're going to end up using in these 2 cases, is pi r squared, and not just sort of saying, well, it's the area of the base. For these, the area of the base is pi r squared. Okay, let's go through the final questions, and then we'll end the video. Give lateral surface area formulas for sphere, cylinder, and regular pyramid. Okay, again, these are not so easy to prove. They're not so intuitive. You just have to memorize them. The sphere is 4 pi r squared. Again, I have 2 dimensions, okay, because again, now we're back to area, 2-dimensional space. The cylinder is actually 2 pi r times h, so it's the circumference or the perimeter of the cylinder times its height. And regular pyramids, just like the cylinders here, you're going to see a correspondence, just like up here between the volume formula for a right prism and the volume formula for a cylinder. You're going to see a correspondence between the surface area formula for a regular pyramid and the surface area formula for a cylinder. So the cylinders is really its perimeter times height. Well, guess what? The regular pyramid surface area is also lateral surface area, I should say, is also perimeter times height. Okay, whatever the perimeter of that particular shape of the base of that prism happens to be, that perimeter times the height will give you the lateral area. Same thing for a cylinder, but for a cylinder, again, since it's a circular shape, we're basing the circumference, the perimeter, on pi. Explain the difference between area, volume, and surface area. Okay, we've basically already done this with area and volume. Area is 2-dimensional space, volume is 3-dimensional space. Surface area is just area of the faces of an object. So again, let's come back to the Kleenex box. The faces are all of these sides of the object that face outwards. Okay, they're literally the exterior surfaces of the thing. So the surface area is all of this area of this side of the thing, plus the area of this side of the thing, plus the area of this side of the thing. Great camera work. Plus the area of this side of the thing, plus the area of that side of the thing, plus the area of that side of the thing. Okay, so we have 6 faces on a rectangular prism like this. So if I add the area of all of those faces up, I get the surface area of the object. Okay, the total surface area. So that would be, normally the total surface area we would say is SA. If I add all 6 sides up. Now, these formulas are for lateral surface area. Again, latus in Latin means it's your side, or it's like your ribs, actually. So, you get a side ache. It's in your latus, okay? Or we have muscles in the side of our back called the lats, okay, or the lateral muscles. It's the same meaning here. Lateral is the sides of the thing. So the lateral surface area means only the surfaces which are not being counted as the base. So these formulas only get us so far. They're not going to actually give us the full surface area of all 6 sides of a rectangular prism or the full surface area of a cylinder. It's only going to give us the side area. If I have, I'm sure I can find a cylinder here. Yes, there's a spool of thread. It's actually perfect. So, if I'm looking down on the cylinder from the top, the base is this circular shape. And on the opposite side, I have the same circular shape. The lateral surface area is not the area of the circle or of the base. It is all of the area around the sides of the thing. Although in the case of a cylinder, it doesn't really have sides. It's just all of this area of this surface, this circular surface around in between the 2 bases. In fact, if I take a cylinder and I cut it, I'll show you this in the next video, but if I cut it vertically like this and then I roll it out and unfold it, I actually just get a rectangular shape, just like a piece of paper. I can roll, I'm sure you've all done this, making telescopes or something. I can just roll a rectangular piece of paper up into a cylindrical object. So here we have, our spyglass, like this. And so the lateral surface area is, again, if I roll it perfectly, or if I cut the cylinder and I unroll the sides, I get a rectangular piece. And the length of the rectangular piece is the perimeter of the circle that I started with. Anyway, we'll come back to that some other time. I'm getting ahead of myself as I usually do. I just can't stop once I get going. Okay, so that's surface area. It's the surface of all of the faces of the object, whatever shape those might happen to be. Okay, get my camera situated again. The L in this formula stands for the slant height. Okay, and the slant height is maybe a little bit confusing. It's not an altitude. It is not a actual perpendicular. So again, if I come back to my cone, so cones and pyramids have slant heights because they have slanted sides going up to the top. If I come back to my cone, the slant height is not the distance from the top of the cone straight down, perpendicular to the base or to the ground, but it's actually a line which runs up the side of the cone. So from the base, going straight perpendicular. It's perpendicular, but it's not perpendicular to everything. It goes up the side of the cone. Oh, not very well drawn. But it goes up the side of the cone like this, from the base all the way straight up to the vertex. Okay, again, my cone is falling apart here. We used to have some little shapes which would make this a lot easier. I'll see if I can find those tomorrow. So that's what we mean by the slant height. And the lateral surface area for a pyramid or a cone is given by this formula, and it depends on that slant height. Again, we're not going to explain why that is just now. Okay, finally, what should we do if we need to find the area of a shape or volume if the shape does not fit any of these categories we've studied? What should be our approach? Well, most of you had the right general idea here. You're going to divide the shape into simpler shapes that you do know how to deal with, and you're going to find those areas, those simpler areas, and you're going to then add them to get the total area. So let's say we have a bizarrely shaped hexagon, something like this. Well, remember we talked about before, the power of the triangle. Well, why is the triangle so important? Because almost any shape can be turned into triangles if you try hard enough. So, if I divide this into all of the triangles that make it up, and not overlapping, okay, not every triangle has to be just touching each other, just only on the edge. And I add all of these small areas together, then I get the total area of the thing as a whole, okay, right? It's very obvious. It's, in fact, it's a postulate. It's one of these things that we can't even prove, and don't even bother to prove because it's so obvious to everyone. Nobody's really going to argue with you if you say that the area of this total thing is the area of all these pieces that make up the thing. Okay, so that works for area. It also works for volume. Hopefully this explanation has helped you understand the corrections on the quiz if you still were confused about anything. And tomorrow I will put together some more videos going into a little bit more detail about where all of these formulas come from and how we can sort of remember them.